Okay, so what we are doing here, just for the repetition over here, we are calculating the efficiency when you have all your parameters. Please remember, at the end, please no talking. We are going to calculate efficiency and all other parameters when you have completed your whole design and you are at plus 4.5% of your percentage Z. Your no load losses and load losses are within your required limits. Then you will carry on towards the other parameters, which are actually the efficiency, the tap calculations, errors, or whatever. The first thing which we have to do is actually the efficiency over here, and as you can see over here, the efficiency is written as output over input. So this means you are actually going to have the output over output plus losses over here. So you are going to find out the efficiency at, the first thing you are going to find out is the efficiency at rated load. So it will be at 100% load, then you will find out the same efficiency at 75% of your load at unity power factor. Then you will also find out the efficiency at 50% of your load at unity power factor, and you will also find out the efficiency at 25% of the load at unity power factor. So these four are actually assuming that your load is actually resistive in nature. Now when I am talking about the efficiency, if I write down the formula here, the efficiency is going to be, we all know, I just wrote it over there, that the output over output plus losses, this is actually the efficiency over there. Now what type of losses are happening inside the transformer? We already know that the one loss is actually equal to the no load loss over there. So this is the no load loss, and this is constant. It's not going to change whether your transformer is loaded or not. It's not going to change. And then I have the I square R losses, or actually the copper loss over there. Now whenever you are talking about the loading of the transformer, you have to do some change in this formula. So supposingly if you are working at transformer at 75% of your load, this means that this formula will actually change into the N multiplied by the output over here, and here it will also change, N multiplied by output plus the no load loss, which will remain the same, plus here now there will be a change over here. This will be N square multiplied by the copper loss, or I square R loss. This N square is coming there because the current is actually having a square dependency on the total losses over there. So when your load is reduced, you have to make it. Now for 75% load, N will be equal to 0.75. So if I go back on this over here, here in this case N is equal to 1, here in this case N is equal to 0.75, N is equal to 0.5, N is equal to 0.25. So this N is actually telling you the total load on your transformer. If it is total rated load, this will be 1. If it is 50% of the load, it will be 0.5, and subsequently whatever value you are assuming. Now in this formula still I have not taken the power factor into consideration, because any transformer, it's not always going to work at unity power factor. So when you have calculated these formulas over here for unity power factor over there, you will repeat these all again over here, and you will actually also find out the efficiency at 100% load for 0.8 power factor over here. Then you will do the same at for 75% load for 0.8 power factor. Then you will have it at 50% of the load for 0.8 power factor. Then you will also find out the efficiency at 25% of your load at 0.8 power factor. So this means that you are actually finding out 8 different efficiencies. Now why 0.8? Now actually the book is using 0.8 power factor, so maybe, I guess I'm not confirmed on this one, because this is an Indian author book, so maybe in India the power factor from the utility company or from the distribution company required must be 0.8. In Pakistan, or if I'm talking about Lahore, or if I'm talking about the electricity being consumed in UET Lahore, we have a penalty whenever our power factor goes down below 0.85. So maybe if this result has to be given out for Pakistan, maybe then you will have this change to from 0.8 to 0.85 over there. And 0.8 is very much not very good power factor overall. If you are in a residential area, 0.8 power factor will be almost there. But if you are in some industrial area, supposingly you have some commercial motors or induction motors there, the induction motors, if they are running at no load, they will exhibit a power factor even less than 0.3. So you will have to use some capacitors over there or some power factor correction algorithm over there, so that you can actually, otherwise WAPDA is going to penalize you because you are actually having a lesser efficiency of your transformer. Now if you are trying to find out for 0.8 power factor or maybe for any other value of power factor, this formula over here will change over there only in this case, that you are going to multiply it by the power factor over there, and for this term also this will change to n into the output into power factor. So this is n NO. Now you have multiplied over here by power factor in the numerator, you have multiplied over here by the denominator also, but you are not going to multiply power factor here. Why? Because this is already I square R losses. There is no need to multiply power factor over there because they are already P losses or active power losses. For those who are still not getting the idea what I am doing over here, if you remember your power triangle, this is P, this is Q, this is S, and this was your angle theta. So if you wanted to find out P, P was equal to S cos of theta. What is S over here in this case? Our S is 100 kVA transformer. So over here in this formula, this is the 100 kVA transformer multiplied by the power factor, you are converting it into watts. And how much load is on that transformer, this N is actually going to tell you that either it is working at 100% load, 50% load or 70% load over there. So this is the general formula over here. So you can use just this formula for the efficiency calculation over here in this case. Okay. Any questions with this? So whenever your transformer is complete, and I hope on Monday when we rejoin back, I hope everyone has calculated your percentage Z, done your previous work, and your percentage Z is fixed at 4.5. The value which we calculated in the last lecture was 4.72. So you have to actually reduce it down to 4.5, and I have told you how you are going to do it. You are actually going to redesign your low voltage winding so that it has a small radial build, so that now then you will have a little smaller B1. Little smaller B1 means that you are going to actually reduce down percentage X over there. And percentage X is reduced, certainly. But yes, certainly you will not be reaching exactly 4.5, but 5 plus minus 5% error is acceptable, but not more than that. So maybe you can have 4.51, 4.52, 4.53, even also a little bit relaxation, but otherwise you have to do this one. When you have done that, then the next thing comes out to be the efficiency, and the very important thing which you have to do over here is actually the taps over here. Now since this transformer has taps also, you have to find out the ratio errors over here. Now I am not going to fill this table, you can do this yourself. Over here I have this 5 columns over here. This is the first 2 rows over here at 5% and plus 2.5. If you see over here in the third column, what we are trying to do over here, we are trying to find out the voltage ratio by having 11 kV on one side, since that is actually connected in delta. So phase voltage and line voltage are same. So I am just multiplying it by 1.05 divided by the phase voltage on the secondary side. So the voltage ratio which I require is 46.2 over here. But by the turns, what ratio I am going to get, I have to calculate it in the fourth column. So what I will do in the fourth column, I know on my secondary side the number of turns are there. I will write that down in the denominator, and in the numerator I will write down the number of turns which I have calculated already, and that will be written over there. Now that value will not be exactly 46.2, it will be something like 45 point something or 46 point something. So in the last column you are going to calculate the error over there, that is between the error values of the third and the fourth column, and that error should be within plus minus 0.5%. Why this table is very important? Because you are actually telling your consumer or the buyer of that transformer that okay, I have given a 5% tap, I have given a 2.5% tap, I have given a 0% tap, I have given a minus 2.5 and minus 5%. But in practical there is an error over there, which means that minus 2.5 is not going to give you exactly minus 2.5, it's going to give you a minus maybe 2.3 or minus 2.4. So this percentage error in the last column is just the error difference in, certainly in percentage, the third column and the fourth column over there. And as written in the footnote, you can see that as per the IS standard over there, it should be within plus minus 0.5% over there. So the values of the third column and the fourth column over here. Now if you remember your transformer we designed over here, since I have taken the same design from your book over here, the same design we followed over there. So can anyone tell me what was the number of turns on the 5% side? Total हमने ऐड किया था, number of turns कितने थे? हाई वोल्टेज साइड की बात कर रहा हूँ मैं जस्ट एक वैल्यू कैलकुलेट करना चाह रहा हूँ. नेक्स्ट वन यू कैन डू इट योरसेल्फ. High voltage winding has total number of turns as 3344, and then you had to add 168 turns for the 5% tap. So 5% taps were having 168 turns. So the total number of turns are 3512. So you, in the fourth column, the first row, you are going to divide 3512 divided by 76. Whatever that value comes out, calculate for that please on the calculator. 3512 divided by 76, it comes out to be, I guess, 46.21. Okay? So now you can see there is a difference over there, 46.2 and 46.21. So what you will do in the last column, you will either subtract 46.21 minus 46.2 divided by, you can take the base of anything. It's totally up to you. You want to take the base either for the standard size. Standard is actually the voltage ratio, the third column, so you can take that one as a denominator. This will give you a percentage error of minus 0.02%. So this is well within the limits as I have just given over there. So if it is less than 0.5%, so it's okay. Now at any point, supposingly out of these 5 rows it is not coming out, then there will be a problem for you. So you will have to again go back, redesign your high voltage winding or whatever. So this is a very difficult task. So when you are actually designing your high voltage and low voltage winding, please take care at that point, because otherwise when your whole transformer is designed and you come at this table and you find out, okay, the percentage error is more than the required limit, then you will have to go back to your high voltage transformer or high voltage winding design, and you will have to revisit it and redraw it. And redrawing it or redesigning it means that the whole process has to be done. Either if it, the core calculation will remain the same overall, but the B1 and B2 or the radial build will change over there. Okay? So this table has to be done whenever the whole calculation is done. So in a similar way you can do this calculation if you have this like 5 taps over here from plus 5 to minus 5% over there. Okay, one last thing before I proceed on further. Anyone can tell me, we have done this in your machines course also, when a transformer gives maximum efficiency? When no load losses are equal to the variable losses. Please remember, for any electromechanical device or magnetic device, not called as mechanical, for electromagnetic device, this is also an electromagnetic device, fan, okay, motor or anything, or a transformer, because you are actually having a magnetic field transfer over there. Maximum efficiency is always when your no load loss is equal to your variable loss. I'm using a general word, variable. Okay. Now variable, if I'm talking about a transformer, certainly this means I'm talking about the copper losses, and if I'm talking about a motor generally speaking, then this means the no load losses are happening, the same core losses and all that in a motor, but variable loss can be different. Variable loss can be the winding losses over there, the bearing losses over there, depending upon the load over there. So that's why I've used this word. So when you are going to have the maximum efficiency, and if you want to find out the maximum efficiency, so the point of your maximum efficiency is found out by no load loss divided by the load loss, and we are going to call this one as K. The K is the same thing as N. K is the same thing as N. N क्या था? N was 1, 100% load. N was 0.5, 50% load. N was 0.75, 75% load. So यहाँ पे आप क्या करो, I'm not going in the proof of this one. This was done in machines. You do visit your machines lectures if you have them. We have done the proof over there. So this K factor is actually going to give you the value of n actually at which you are going to have the maximum efficiency over there. Now in our case, if you remember, what was the no load loss in our transformer? Our no load loss last lecture. No load loss कितना था? Just I want to find out the K here in this case. 250.2, 0.34. Okay, and what was the load loss? 1760. Please calculate this K factor. 250.34 and 1760 in the denominator, take square root. 0.377. Now what this is telling you? This is actually telling you that a distribution transformer is going to have its maximum efficiency at 37.7% of the load. Now, since still you are just students and you have not gone in the industry or the field specially, you will have, if you supposedly go to a distribution company such as Lesco or Gepco anywhere, you will find out that a distribution transformer, if you have a chart over there, it is majorly for at least from the morning time at 9 AM or 10 AM up till 5 or 6 PM, it is almost at the same load, 30 to 40 or 45%. Only at night time when you have actually, or the evening time when you are actually having more televisions on, everything is on, air conditioners are on, the load is different. Otherwise, the distribution transformer is going to exhibit a normal variable load of something 40 or 35 to 50% range over there. So in this case, you are getting a 37.7%. So what this means, if I want to make a small graph over here, I hope some of you will still remember this graph, but we have done this in the machines also. So in this graph, this was the no load loss, and this is constant over there. And if you remember the load losses, and here this is the IS current is increasing over here. So this was actually going to this will actually go a lot faster over there, like this. This is your load losses. Now the point at which they both are same, as you can see, when the point at which they are actually going to have, and if I redraw it with another color over here, so this means that my efficiency is going to be actually like this. It's going to exhibit the maximum efficiency at this point. So, and that point over here, according to our calculation, it is coming at 37.7% of your load. So this curve over here is actually for the efficiency, and the other two curves are the no load loss over there, and then there is the load losses. So you can say that this is actually on this one I have the losses over here, and I have another curve line over here. This is actually the efficiency axis over there. Okay. So this is actually just telling you. Now when you know, when you know your maximum efficiency point, आपको निकल गया, it's 0.377 over here. Can you find out me the maximum efficiency now? अभी हमने सिर्फ पॉइंट निकाला है कि मैक्सिमम एफिशिएंसी होनी कहाँ पे है, मैक्सिमम एफिशिएंसी नहीं निकाली अभी, वो कैसे निकालेंगे? The same formula which we have done just now, this formula here, you are going to put 0.377 and here also 0.377, and again you are going to assume either a power factor of 1.8. It's totally up to you that what power factor you are having a load over there, then this will give you the maximum efficiency over here. Okay? So in the same formula here, instead of n you can just write the variable k, or you can just directly put in 0.377 and this will give you. Now why this is required by the consumer or the person who is actually buying this transformer? The reason behind it is because he should know that the transformer is going to exhibit the maximum efficiency at what value over there. Now, if the same transformer was designed as a power transformer, this value of 0.73777 would not be actually in the very small range. In that case, it will be something near about 0.6 to 0.7. Why? Whenever a generator is on, it is almost giving 70 to 60% of the power to the national grid. Okay? It's never kept at 30 or 20 or 40% of the power majorly. अब खैर ऐसा नहीं है कि आप किसी पावर प्लांट को रन ही हमेशा मैक्सिमम एफिशिएंसी पे करेंगे. देयर आर सम क्रिटिकल पॉइंट्स और क्रिटिकल junctions where you are going to run it at the lowest efficiency also. But this is the duty of a power plant engineer at that point. He has to actually find out that which plant is actually the most cheapest and the most best to run at that particular time. And for the very same reason, our UET, when we had those gas turbines over there just beside the main block, we have seen our power plant, we erected 3 power plants over there. One was 1.5, one was I guess 1.2, and the other last one was 0.7, I guess. So the total installed capacity was 3.1. Now the major question asked was over there, why not we have not installed one generator over there? The reason very simple over there, because in the morning time we have all the classes on, everything, so we can on all 3 generators or maybe 2 generators depending upon our AC load over there. But at the evening time, no classes are happening, only the colony or maybe just little MSc classes are going on if they are in the evening. So maybe we can just run a very small plant over there. So in this way you can actually run your generators or plants at the maximum efficiency. ठीक है. खैर उस ज़माने में हमने जब ये प्लांट लगाया था, our university was the first university in whole of Pakistan that was having the gas turbine station. But now since gas is not there, now it's totally मुझे नहीं पता शायद उसको अब वो scrap में जाएगा या कैसे जाएगा, but it's still unusable. We have now a diesel generator which is actually giving the power in load shedding time. और ये उस वक्त का दौर है. We had 2 feeders in UET at that time, and those 2 feeders were based on this purpose. One was coming from, I guess, from the Shalimar Garden, the other one was coming from here, the Giri-Shahu region. So when we were having एक ब्लॉक होता था, हम दूसरे से ऑन कर लेते थे. हमने उस वक्त थोड़े से प्राउड में आते हुए हमने कहा अपना पावर प्लांट लगा दिया, हमने एक की छुट्टी करा दी. तो अब वो हमें अगला फीडर अब देते नहीं है. So we have now load shedding, and for that load shedding purpose, we are actually producing the diesel power generation approximately, I don't remember the today price, but I guess 1 or 1.5 years back, the unit price was 39 rupees per unit. So there is a huge amount of money being spent just on this because it is diesel. It's a diesel generator, and a diesel generator is always very expensive because of the price of the diesel and whatever. Any questions with this, G? So you can find out the maximum efficiency by this one and total overall. Anything from here, because then I can start the quiz. And most probably transformer design is complete from my side from chapter number chapter number 5. Okay, one thing very important, chapter number 5 is the design of a 100 kVA transformer. Chapter number 6 is the design of a 630 kVA transformer. This time I changed this one. In 2013 session when I taught this course, I did a 630 kVA transformer. This time I have changed it to 100 kVA. Go through chapter number 6 yourself. It's the same thing. Okay? Just is the only change is this, that the size of the transformer will be large, the window height will be large, the winding ratings will be large, or the capacity will be large, the current density will be different, and we have designed an aluminium transformer. In 630 kVA, you are designing a copper transformer. Now, when you have done this one, in the next lecture, I will most probably go with the percentage X proof from R.K. Agarwal book, and then I will go towards the tank design of your transformer. And as soon as I have done the tank design, I will proceed to chapter number 7, which is actually a power transformer design. That is a 5 MVA, that is 33/11 kV transformer over here. And we will not go in that much depth inside this one because this book is not giving that much depth, but still I will give you a little bit data on how it is different from the distribution transformer, especially for 5 MVA range over here. Now 5 MVA is a very small transformer, not very big transformer. If you have gone to Tarbela and Mangla, the one unit over there, if I am talking about Mangla over there, it is a 100 MVA one unit. one generator over there. So one generator, if it is 100 MVA, so you at least have to add a 100 megawatt transformer over there. But in this chapter, they are only designing a 5 MVA transformer. So certainly it will be a power transformer. It's not 400 volt level. It is 5 MVA over here. And if by chance after this today's lecture, if there is a lockdown or something, education institutions are not open, then hopefully we will meet online. So that's why actually I was also not feeling well today, but I came just for